Let's get started. Um, so today, what we're going to do is spend the first half covering more of RDT, and then the second half open it up to questions. We have written exam number one for this class on Thursday during class period, and like is usual for my exams, well, not all my exams, but for this class, you're allowed one 8.5 by 11 sheet of paper, both sides, on which to put your notes, anything that you find useful, and use it on the exam. Fair game is everything up to and including last Thursday's material, which is RDT 2.2. Certainly, the material will more emphasize from the application layer as well as Chapter 1's material. We will cover content delivery networks, we will cover caching, we will cover application aspects, we will cover everything is fair game. So question-wise, probably be about five, maybe six questions. So please make sure you understand how things work. And as far as RDT 2.2 is concerned, I will ask you a question about what's happening in the finite state machine. So please make sure that you understand how all of that stuff works. Okay, any questions about that? No? Okay, so let's continue on where we left off. And so written exam number one is the 27th of February. Where we left off, we talked about RDT 2.2. And what RDT 2.2 did is it took these sequence numbers on the acknowledgements, the so-called knack-free version of protocol, and it added error checking to it. And so there's the finite state machine, and the finite state machine had four states, and they only give you two of them in the book for the sender and receiver fragments. This is the sender depicted. And so the other two parts of the fragments that are missing are wait for call from 0 above, which is down, which would be down to the right, and wait for ACK1, right? And so we start out in the start state, which is this dotted arrow. We wait for the event RDT send. So some application has called send, like an HTTP GET message, sending it to the transport layer. It creates the packet, computing a checksum using the message data and using sequence number 0. So it does the UDT send, this unreliable send, and then it transitions to waiting for the acknowledgement for 0 to come back to it, to come back to the sender. And so one of two things can happen. Either it gets the acknowledgement, the sender gets that feedback for the ACK for packet 0, or it does not. And so the self edge here, that first edge that comes back to wait for ACK 0, RDT receive is called, or that event occurs. So that means that data comes in to this transport layer from the network layer below. It checks it to see one of two conditions. Is it corrupt? If it is corrupt, then it resends its packet. Now, of course, you need some buffer space in order to save that packet because you might need to resend, you being the sender side transport layer. So if it's corrupt, you do UDT send, you resend that packet that has been saved. And if it is an ACK, it's not corrupt, but that ACK is not acknowledgement for packet 0, then it's going to also resend. Okay, so then the other edge, that means it got the ACK that it's waiting for. So RDT receive occurs, that event. So network layer delivers a segment to the transport layer at the sender side. It's not corrupt, so that means the stored checksum and the calculated checksum equate or equal to one another, and it is the correct ACK. Right, so then it transitions to wait for call 1 from above, and that whole process continues, alternating between the wait for call 0 from above and the wait for call 1 from above. So you do a wait for call, send the segment down into the network layer, you wait for the ACK for that packet, and then once you get that ACK, you now wait for the call from above again. So it's a send and then wait for ACK, a send and then a wait for ACK, and that process repeats itself. On the receiver side, we have two states. Wait for 0 from below, and it's below because on the receiver, you're waiting for that segment to come in from the network layer below through the unreliable transport. And then you also have a wait for 1 from below. So on the receiver side, you're waiting for sequence number 0, packet stamp with sequence 0, and then you're waiting for packet stamp with sequence 1, and you keep alternating between these two states. Now, waiting for 0 from below, one of two things can happen. You either get 0, sequence number 0, or you don't. Let's take a look at what happens if you don't. Now, conceivably, you have already sent this ACK with 1, and now you're waiting for sequence number 1 to come back, or sequence number 0 to come back. So one thing that can happen, you get your receive event, you check to see if it's corrupt, and then you check to see if it has sequence number 1. Now you're waiting for 0 from below. You're not waiting for 1. So if you get sequence number 1 as a receiver, you're going to resend that ACK, right? Because you've already acknowledged 1. The other thing that can happen to cause this transition out of wait for 0 from below, you get the RDT receive, it's not corrupt, and it has sequence number 0. That's going to cause you to transition for this edge to that other state that's not depicted, transition to wait for 1 from below. Does that make sense? Any questions about this? Okay, so that's where we left off. Okay, continuing on. And so we're going to go to RDT 3.0. And there are going to be some new assumptions, and now we're going to bring in the full treatment of the unreliable channel, which sits beneath the transmission layer. And so certainly we had a bunch of mechanisms in place. We have checksums. You can check for corruption, corruption both in the data that's going on the forward path from sender to receiver. You can have corruption on the acknowledgement, right? And that's what RDT 2.2 added. You also have these sequence numbers that allows you to know what packet you should expect to receive next, right? And also expect to send next. And those were helpful, but when you introduce congestion, the idea that packets can take a really long time because there's congestion at the routers, or in the worst case, packets can be dropped altogether. Now you need some other resources in order to guarantee reliability. And so that resource is a timer, right? And that's another resource you need when you want to engage in reliable end-to-end transport. And so in using a timer, essentially what that timer encodes is some notion of a reasonable amount of time for which the sender should wait in order to get an ACK. And so the sender now will send a segment, and then it'll wait some amount of time. And if it doesn't hear back from the receiver, i.e. if it doesn't get an ACK within that amount of time, it's going to assume that it was lost, and it's going to resend. And so this does two things. It allows you to recover from congestion or packet loss, but it also introduces an issue. And that issue is if that packet has not been dropped, but it's just taking too long. That's both on the forward path, sending that request, and also on the reverse path, getting back the acknowledgement. If that packet takes too long, and then you end up resending, you can end up with duplicates now, right? So you also need to add the handling of these duplicates. Now, certainly on the receiver can already handle duplicates. It just takes it, doesn't deliver it, and then just goes along merrily, waiting for the next thing to happen, right? But on the sender side, you now need to handle these duplicates, these duplicate acts that can occur, okay? And this requires a so-called countdown timer, and there are many ways to implement it in an operating system runtime. But you're going to have now a timer associated with a packet that you send, and that timer is going to measure some notion of a reasonable amount of time in which to wait, after which you can assume that a packet was lost. Okay? Any questions about this? All right. So let's take a look at the sender side, and the receiver hasn't changed. It's just the sender that's going to change. And it looks pretty complicated, but it's not so much. You now add these timers, and you'll see on the decorations associated with the transitions for this finite state machine, you see conditions associated with the timer. So again, you always start out with wait for call 0 from above, and it's going to alternate between sequence 0, sequence 1, sequence 0, sequence 1. So what does it do? It sends the packet with sequence 0, and then it waits for the acknowledgement for a packet with sequence 0. And then once it gets it, it sends a packet with stamp sequence 1, sequence number 1, and then it waits for acknowledgement for 1. So you always know that it's send 0, wait for ACK 0. Send 1, wait for ACK 1. Then go back to send 0, wait for ACK 0. And then all the edges are the things that can happen when it's not successful. So we start out a wait for call 0 from above. So here we have the sender runtime waiting for some application on the sender side to do a socket send. So that event occurs, the RDT send with some data. So what happens? So you create a packet, and that packet is going to include a checksum, the message data, and it's also going to include sequence number 0. So then you save a copy of it. That's what that send packet equals, what that means. So you need some buffer space. Then you do the UDT send with that packet you just created, but it's still stored in buffer space locally because you might need to resend it. So then immediately after doing the unreliable send, the sender side starts a timer, right? So that clock starts ticking. And then it transitions to waiting for acknowledgement 0. So this is the wait part. So you send packet of sequence 0, and then you wait for the ACK for 0 to come back as feedback from the receiver. So what can happen when you're waiting for ACK 0? Well, a number of things can happen. Either you get the ACK 0, great, then you transition forward to the next state, wait for call 1 from above, or one of these two self-edge cases. The top self-edge corresponds to corruption, or it's the wrong ACK, and the next self-edge, that middle self-edge, corresponds to the timer. So let's take a look at the top one. So you get RDT received, so data comes inbound from the network layer below. This is the transport layer. You check to see if it's corrupt. If it is corrupt, then you do nothing. You just drop it, you don't do anything with it, and then you're still waiting for ACK 0. Okay, now the other part of that condition, you get the RDT received, so you get data from the network layer, and you find that it is an ACK, so it's not corrupt, but it is an ACK, but it's the wrong ACK. You're waiting for ACK 0, and you got an ACK with sequence number 1. So what do? You do nothing with it. You just take that data, do nothing with it, throw it away, and just continue to wait. Okay, so let's look at the next case. Well, you're waiting, waiting, waiting. There's a lot of congestion, and that congestion makes it so that maybe that ACK is taking a really long time, or maybe the ACK was lost altogether, right? So the timeout expires, and so you get a timeout event. And what happens? Well, you do a UDT send, so you're resending that packet, you the sender, because you safely assume, because you haven't got an acknowledgement in a long time, the timeout expired, you assume that it was lost and you resend it. So you do a UDT send with that saved packet with sequence number 0, the data in the checksum, and then you restart the timer, and now you're waiting once again to get that acknowledgement where the ACK is stamped with sequence 0. Does that make sense? Any questions about this? So again, it's a send with sequence number, wait for that sequence number. Send for that sequence number, wait for that sequence number. So let's look at the actual transition edge. And so RDT receive is called. You get the data from below, the segment. So it was delivered to you at the sender. So that's going to be feedback from the receiver. It's not corrupt. You check, you compare the saved checksum to the calculated checksum. And you check to see if it's an ACK, and it is an ACK with stamp 0 on it, sequence number. So that's all true. So what do? You stop the timer. You've gotten the acknowledgement you've been waiting for. And now you transition to wait for call 1 from above. Now, when you're waiting for call 1 from above, you might get duplicate ACKs, right? They just start coming in. If you get RDT receive from that, from at that point when you're waiting for call 1 from above, that means you've been getting ACKs that are duplicates, right? And so you take in these ACKs and you just do nothing with them, throw them away. So now what you're waiting for is a call 1 from above. So any duplicate ACK you get here is thrown away by the sender, right? You've already acknowledged ACK 0, you've moved forward, now you're waiting for call 1 from above, a new send from the application layer. And so you get this RDT send of the data, you create the packet with the checksum and sequence number 1, and then you do the unreliable send and start a timer. Now this timer is for that packet that you sent with sequence number 1. And again, you come here and you're waiting for the ACK. Now I won't go through all of these. What I will do is look at the timeout, right? The timeout fires, that means you haven't gotten ACK 1. So you do a resend, and that resend is of that packet stamped with sequence number 1. You've saved that aside just in case you need to resend it. So then you're going to stop the timer if you get the correct ACK. You get RDT receive, it's not corrupt, and the ACK number is ACK with sequence number 1. So you're going to stop the timer, and now you're waiting for call 0 from above again. Okay? All right, any questions about this? Does that make sense? And so in all cases, you send something, and then you wait for the ACK. You send something, and then you wait for the ACK. When you're waiting for the ACK, a bunch of things can happen, and you need to respond to that. Once you send something, right, a bunch of things can happen. After that transition, you send something, you're always waiting. So you send causes a transition, wait for the ACK. evaluate all the different contingencies that can occur. Okay? All right. Any questions? No questions? All right. So let's take a look at RDT 3.0 in action. And this is the full-blown treatment of reliable data transport. RDT 3.0 takes RDT 2.2 and it adds these timers so that you can handle issues concerning congestion. Excuse me. So in these network diagrams, we have a sender side and a receiver side. The sender is the left-hand column, your left, and the receiver is the right-hand column. The sender is in blue and the receiver is in green. Now, when you send messages, a message that goes from sender to receiver will be noted by an arrow going from left to right, and then an arrow from right to left will be feedback, i.e. the ACK, from the receiver going back to the sender. And in these network diagrams, as usual, time increases as you go down the board. And so there are two frames here that consider two different scenarios. One is if there's no packet loss, and the other if there is packet loss. So that means you send data, there's congestion in the routers, those queues fill up on the routers, and then a packet comes in, there's no buffer space in which to store them on the routers, and so they get dropped. Okay, so let's take a look at the case with no loss. So the sender sends packet 0, and the receiver gets packet 0 and sends back ACK 0, right? So that's ACK with sequence number 0. And so the sender is now, once it sends packet sequence number 0, it's now waiting for ACK 0 before it proceeds in sending the next one, right? And so the sender gets ACK 0, and now it sends packet 1 across the wire to the receiver. The receiver gets packet 1, it sends ACK 1. The sender gets ACK 1, now it goes back to sending packet 0. And the sender does not proceed after sending packet 1. It does not proceed until it's gotten that acknowledgement for packet sequence number 1. Does that make sense? And so this alternating protocol, right, it's called stop and wait, in that the sender, it does something and then it stops and waits for that acknowledgement and does not proceed until it gets the acknowledgement with the correct sequence number that it is looking for. Okay? All right, any questions about this? All right. So now let's look at the case where you have packet loss. And so you send a packet from the sender to receiver. It gets back an ACK. So the packet 0 gets sent, and the receiver gets packet 0 and sends back an ACK. And so the sender gets that ACK 0, and now it can proceed, and it sends packet 1. So now all of a sudden, packet 1 hits some router, and the router's buffer space or queue is full, and so that packet 1 gets dropped. So you get packet loss. So here you have the receiver. The receiver is just waiting, doing its thing. It's not getting any packets, so it's not sending any acknowledgments. And the sender, once it sent packet 1, it's now waiting for ACK 1, but it sets that timer. So now that timer continues to tick, and eventually the timeout occurs, and in that time, during which the timeout transpired or expired, went to 0, no more time left, it safely assumes, or one can safely assume, that there must have been some packet loss with packet 1. Otherwise, it would have gotten the acknowledgement. So the sender, once that timer expires, it resends that buffered packet 1, and that buffered packet 1 makes its way to the receiver, which then, in response to getting that packet 1, it sends back ACK 1. Sender now gets back ACK 1. It proceeds forward to send packet 0 using RDT send from above. Okay, any questions about this? Okay, so we have, from the sender's perspective, it's stopping and waiting for ACK 0. It sends packet 1 and then stops and waits for packet 1. The timeout occurs, causes the resend, and then it waits for ACK 1, gets the ACK, and proceeds. Okay, so let's take a look at two other scenarios. Well, that talks about packet gets through successfully, and then we looked at the packet being lost. We could also have the ACK being lost. So that means that feedback from the receiver going back to the sender, that arrow going from right to left, that gets lost, right? So let's take a look at this. So we send packet 0. Packet 0 makes its way to the receiver, and the receiver sends back ACK for 0. So here's our ACK 0 coming back to the sender. The sender then proceeds forward with sending packet 1. So packet one goes across the wire to the receiver. The receiver gets packet one. It sees that sequence number and constructs an ACK1 that it sends back across the wire. So this ACK makes its way to a router along the route between the receiver going back to the sender. It meets a router that has full buffers, so no more queuing, no more space in the queue left to store this ACK. So it gets dropped. So that ACK is lost, and in the meantime, the sender, his timer, is now waiting. Eventually, that timer fires, and the sender has not received in that time that has transpired. It hasn't received ACK1, so it safely assumes that maybe packet one was lost. Now, was packet one lost? No, it wasn't. The ACK was lost, but the sender doesn't know this. So the sender just blindly follows the protocol and says, okay, if I haven't heard back from the receiver in a certain amount of time, I resend my information. So the sender resends packet one. Packet one makes its way back to the receiver. Now you notice here on the receiver side, this packet one is a duplicate, right? At that point, the receiver, it sent back ACK1 and it saved that ACK. And if it gets packet one again, a duplicate, it resends that ACK, right? But it does not deliver that packet one, right? It doesn't deliver it, but it sends back the ACK that it most recently sent because it saves it on the receiver side. So when that second occurrence of packet one is received due to the timeout, from the receiver's perspective, that's a duplicate of packet one, right? That's like you get the same video frame 2 times in a row. Now, underneath the covers, what the receiver does is says, okay, well, I've already gotten this. I'm now waiting for packet zero, not packet one. This must be a duplicate, so I'm going to resend the ACK that I most recently sent, and it's an ACK for one. So then this ACK1 makes its way across the wire, and it is not lost. Maybe the congestion clears itself up on the routers in between the receiver and sender, and so that ACK1 makes its way through. The sender gets ACK1. Now, the sender thinks that this ACK is in response to that duplicate. It doesn't know. It doesn't matter. As long as the protocol is sound, it works, right? And so this ACK comes back to the sender, and now the sender got that acknowledgement for packet one, and it proceeds forward in now sending packet zero, and this interaction continues. Okay. Any questions about this? Does that make sense? All right. So lastly, the other thing that can happen, now congestion is the absolute extreme. That's when a packet gets dropped, but you can have buffers on the routers between the sender and receiver that are close to being full. And the more full these buffers are, the longer packets will have to wait in line before they're transmitted out the outgoing link to the next hop, across the next hop. And so this last one is a premature timeout, or so-called delayed ACK, that something hasn't been lost, but it's just been taking a really long time. Okay, so we send packet zero, and the receiver receives packet zero and sends the ACK back across the wire as feedback to the sender. The sender gets ACK zero, so it moves ahead, moves forward in sending packet one. Now, of course, on every packet send, the sender is setting a timer. So it sends packet one and sets a timer. Packet one makes its way across the wire, and then maybe a lot of people watching Game of Thrones on Netflix or whatever, it gets packet one. All of a sudden, there's a lot more congestion on the network. Now, of course, the router buffers aren't completely full. They're mostly full, but there's still a little bit of space, meaning that any new arrival packet on the router's queue, it will take a really long time or much longer time for it to be serviced and transmitted out the outgoing link. And so this ACK1 is sent back as feedback by the receiver to the sender, and this ACK takes a really long time to make its way back to the sender. So from the sender's perspective, if this timeout expires before that ACK arrives, the sender has to assume that something must have gotten lost. Well, it hasn't gotten lost, but it looks the same as if it were lost because there's no way of telling. And so once that timeout expires, the sender resends that packet. Now, in the meantime, it resent that packet, and eventually that ACK arrives, right? And so from the perspective of the receiver, that second send of that packet, when the timeout expired, packet one, is a duplicate from the perspective of the receiver. And again, the receiver has already gotten packet one, it's delivered it, so any new occurrence of packet one, assuming it's a duplicate, it does not deliver it, right? It just drops it on the floor, so to speak. And so it detects that duplicate, and then, and this is where it gets a little weird. So it detects the duplicate in the receiver, and then it sends ACK1. So it says, okay, well, you resent it, but here's the ACK because I'm getting it as a duplicate. And the difference between the first time when the receiver got packet 1 and the duplicate is that when the first time the receiver got packet 1, it actually delivered that packet to the application above. The second time it does not deliver, but it still resends that ACK1. Okay? So in the meantime, well, the first ACK1 from the receiver, it finally made its way after the timeout fired. And after the timeout fired for packet 1, it resent packet 1 from the sender's perspective. And then all of a sudden it gets ACK1. So then it goes forward in sending packet 0. And from the sender side, it does that alternating. So it got ACK1, so it sends packet 0, and then waits for ACK0, and so forth. But in the meantime, well, here, the sender got the duplicate, sent ACK1. So packet 0 came across, and then it's sending ACK0. And then packet 0 came across, and it eventually it catches up, right? And so packet 0 comes across as a result of sending packet 0, and the receiver just got done sending ACK1, and so it got packet 0, sends ACK0. So now you have ACK1, ACK0 in a short succession. And so ACK1 came across, was received at the sender. It then goes to send packet 0. Packet 0 goes across. At the same time, ACK for packet 0 comes across. So at this juncture, right, the sender thinks, hey, this thing's really responsive. I sent a packet 0 and I got ACK0, right? But it's not for the same packet 0 instance, right? But eventually these things catch up. And this issue I'll address more specifically when we talk about windowed protocols. We'll talk about the sequence number space and how you select your sequence number space. But nonetheless, this stop and wait happens in the sender. And even if you get a duplicate, you're going to resend that ACK, and then eventually they catch up to one another, and you're now synchronized in this send, acknowledge, send, acknowledge, send, acknowledge. Okay? All right, any questions about this? Does that make sense? Okay. So let me check the time. And 12:28. Okay, we're to 1:15. So I have about maybe 10 or so more minutes. Okay, so let's take a look at what happens in RDT 3.0. And RDT 3.0, it's more of a theoretical thing. I mean, it has all of the ingredients of a reliable data transport, but it makes lousy utilization of your available bandwidth. And this lousy utilization has to do with the protocol itself and nothing with the underlying link bandwidth. And so it's correct, but the performance is horrible. And let's assume we have a 1 gigabit per second link. Right, that's pretty fast. Gigabit, you know, FiOS can do 1 gigabit in Delaware at least right now. You can get that for a home environment. And so let's assume that your propagation delay is 15 milliseconds, which is typical, and you're trying to send an 8,000 bit packet. So 8,000 bit is 8 kilobit or 1 kilobyte, right? So if you say 1 kilobyte, a byte is 8 bits. And so it's really important to make sure you pay attention to the units in this case. So if we have an 8,000 bit packet and our link capacity, transmission rate, is 1 gigabit per second, giga is 10 to the 9, mega is 10 to the 6. You kind of go in 3 increments. Kilo is 10 to the 3. And so you have 8,000 bits over 10 to the 9 bits per second. It's 8 times 10 to the minus 6. Or 8 microseconds. Micro is 10 to the minus 6. Milli is 10 to the minus 3, right? Nano is 10 to the minus 9. And so we have 8 microseconds is the transmission delay associated with this scenario. So that's pretty fast, right? You might think it's fast, but the issue has to do with this propagation delay and the round trip time. And so this idea of utilization talks about what percentage of the time are you actually using your channel to send actual data, right? And so what happens here? Well, in this case, you send that 8,000 bits, right? And that's some time. And when you send these 8,000 bits, when you're transmitting it, well, what happens? It propagates across the wire. It takes 15 milliseconds to do that. And then the ACK propagates in the reverse direction, right? So that's another 15 milliseconds. So in total, even though it takes you 8 microseconds to transmit this data. In addition to transmitting this data, it has to propagate down the wire from the sender to the receiver, and then the ACK has to propagate back across the wire from the receiver back to the sender. So the total time that you spend communicating is the round trip time plus the transmission rate, right? Because in order to send this and receive it, you have one 30 millisecond, another 30 millisecond, that's your round trip for the message to go to the sender and the ACK to come back in the reverse path. And then you have L over R is the amount of time you spend transmitting this 8,000 bits. Now, that's the total time it takes for this message to be considered successfully sent, because you include the cost time-wise of the acknowledgement in addition to the propagation. Now, out of that total time, L over R, many seconds, is spent actually physically putting data on the wire, right? So in the numerator, we have the amount of time spent transmitting the data, that's 8 microseconds, 0.008. And then in the denominator, we have the total time. We have 30 plus that 0.008. So if we look at that, that's a really, really small percentage of the time that you're spending actually putting data on the wire per round trip, right? Now, if you consider a 1 gigabit per second link, well, you take your 30 milliseconds and you can multiply that 33 times, right? So that's about a 33 kilobyte transmission rate. So here it is, you purchased a 1 gigabit per second link. Maybe you pay the 100, 150 to Verizon Fios a month to get this gigabit link, and you're only effectively sending data at a rate of 33 kilobytes, right? That's 33 kilobytes was from the days of old dial-up modems, right? Which wasn't that old, but you're wasting your network bandwidth. And in this case, there's nothing you can do about it because it's the protocol itself that is limiting your usage of this wonderful 1 gigabit link, okay? So what do you do to alleviate this? Well, instead of just sending one packet at a time, send more than one packet at a time. And so you're increasing your utilization by sending more units of data. And when we looked at RDT 2.2 and all the RDTs ending and including RDT 3.0, I said it was a so-called stop and wait protocol. Yes, it's reliable data transport, but it sent a packet with some sequence number and then waited for the acknowledgement for that packet before it could send anything else. Now, with the stop and wait, this depicts this same number that we calculated for utilization. You start out at some time t, and at L over R, which is the transmission delay, which is in this case 8 microseconds, you transmit your data, your 8 kilobytes, your 8,000 bits, 8 kilobits into the wire, right? So at 8 kilobits or L over R, that's the amount of time for your transmission delay. So now your round trip time was the amount of time it takes for your message to propagate, that was 15 milliseconds, to the destination, and then the acknowledgement, and we don't count the transmission of the acknowledgement because it fits in one packet, and for the acknowledgement to make its way back, and that takes 15 milliseconds. So the RTT, or round trip time, is 15 milliseconds from sender to receiver, and 15 milliseconds for the receiver's feedback, i.e. the ACK, back to the sender, okay? So we take that time and we add it to the L over R, and now at time RTT plus L over R, you're only sending one packet, or the 8,000 bits worth of data. And so to speed things up, what you do is instead of sending just one packet during that first round trip time, this time here is wasted. You're just waiting. You're not doing anything as a sender. So why not fill this time with transmitting other packets? Right, this RDT send from above. And that's exactly what so-called pipeline protocols do. Okay, so pipeline protocols, what are they? And so instead of having one packet in flight, now this word in flight means that that packet has been transmitted and it's now propagating its way down the wire. Now, going back to the previous diagram, during this time, that 15 milliseconds plus 15 milliseconds or 30 milliseconds, the sender's not doing anything. So if the sender's not going to do anything anyways, why not use that time transmitting more packets? Because this packet has been fully transmitted and now it's making its way down the wire. So by sending more packets during that idle time, instead of just sitting there doing nothing, waiting for the ACK, you can now get better utilization of your channel. And when you do that, that's called pipelining, right? And so pipeline protocols allow the sender to have multiple in-flight packets, multiple packets that are in different stages of going down the wire or in transmission. And so if you have multiple packets in flight, that means they have not yet been acknowledged, because you can only be acknowledged once you are received at the receiver. Now remember, in a real network, when you're sending packets, well, one packet might be between you and the first router. The other packet might be between the first router and the second router. The other packet might be in the buffer of the third router. The other packet might be on the other side of that router where the other ones are waiting. So you can have multiple packets that are in flight, meaning they're in some state between the sender and the receiver, but they have not yet been acknowledged. And when you pipeline, essentially what you do is you say, okay, I'm going to make use of this idle time on the sender to transmit more than one packet at a time. And in doing so, more of that time I'm going to spend actually sending data instead of just idle waiting for the acknowledgement. And so with this pipelining, now instead of having a single sequence number, send packet number 1, then 0, and then 1, and then 0, I'm going to have more than just that 2 sequence numbers. I'm going to have a whole range of sequence numbers. And what these ranges of sequence numbers are going to connote is the packets that are in flight. They're in some state between the sender and the receiver. They have not yet been received by the receiver. They're in flight, but yet they have not been acknowledged, right? And so I can have multiple in-flight yet unacknowledged packets, and I'm going to have a range of sequence numbers beyond just this alternating between 0 and 1. So now I'm going to have an integer, right? And now I need to add buffering, right? Now before, the storage that we talked about only stored a single packet. You store packet 1 or you store ACK 1. You store packet 0 or you store ACK 0 because you not need to reset. Now at the sender side, if you're going to have multiple packets that can be in flight, now you need to have a buffer we can store some number of packets. So you're going to have to be able to store an array of packets instead of just one. At the receiver side, because you can get these packets delivered to you in an arbitrary order, right? Now you need a buffer to now assemble all of these packets that you can receive that are in flight. So if you can send up to 10 packets at a time, great. Now you need to have a buffer that can hold 10 packets worth of data at the receiver side, because you need to assemble these packets in the right order. What order do you assemble them in? Well, that's what the sequence number is for. So it's in order sequence 0, sequence 1, 0, 1. If we had sequence numbers 0 through 9, we'd get packets 0, 1, 2, 3 up through 9. And then when we receive them at the receiver, if they don't come in that order in which they're sent, you assemble them based on the order of the sequence numbers. And only then do you deliver them to the application above. Does that make sense? Any questions about this? Okay, so yes? Ah, you wait. You don't deliver. So if you had 0 through 9 and you're missing 2, that means 0 and 1 were in order. So you deliver the 0 and 1, and then you just wait for 2. And so it only delivers up to those that are in sequence, and everything that's not in sequence, it waits until all those gaps are filled in. And we'll see that when we talk about the two different categories of pipeline protocols. Um, so there are two major categories of pipeline protocols. One's called go back N, and one is called selective repeat. Let me check the time. I don't read upside down very well. 12:39. So we're at 1:15. So I'm going to stop here, and we'll pick up with this again a week from today on Tuesday. And then I guess the following week is spring break, right? So yeah, so I'll stop here. This is a good stopping point. And so these pipeline protocols increase utilization of your channel by exploiting that idle period during the round trip time when the sender would otherwise wait. It's now sending multiple packets. And when you do that, it means you can have multiple packets in flight, meaning they have not yet been acknowledged. And the consequence of that, well, the benefit is that you increase utilization of your channel because you're pushing more data down the channel per round trip time. But the engineering consequence of that is now you have to have buffering for an entire set of packets instead of just one at a time. And on the receiver side, you use that buffer to assemble those packets in order, and you do not deliver unless they're all in order. And on the sender side, you use them to hold them to then resend ranges of sequence numbers should you find that something is not delivered or you don't get acknowledgement for it. Does that make sense? Okay, so we'll stop there and we'll pick back up on Tuesday with the two different major approaches. One's called go back in and one is called selective repeat. Okay? All right, so we'll stop there.